Can everybody hear me?
Yeah, you sound good.
Okay, my name is Ken Warfield. I've been with Shawnee State University, teaching in the electromechanical area for 32 years. I retired this past June, and now I'm back as a temp, still teaching in the electromechanical, but I think that's just going to be for this one semester. At least I hope it is. Prior to teaching, I've got about 10 years of industrial experience, and then throughout my tenure with Shawnee State, I've done a lot of consulting jobs on the side. So I've been doing this for quite a while. What I would like to do is talk with you about how we deliver the DC course at the college level, to give you some idea of the rigor and the depth of coverage that we would expect. What you're doing on your career tech side is you have to do a shift of your mindset when you're teaching this course, that you're not teaching at the high school level, because you are teaching a college course, because the students are going to get college credit for it. So when your student would come to us, we're expecting them to have the same level as our students when they completed the course. So they're both ready to start the second course in the electrical sequence, which would be AC. And with that in mind, it's a lot different than teaching just at the high school level. And at the high school level, what I've noticed, we've been doing articulation with tech prep and career centers now for at least 15, maybe crawling towards 20 years. And I've noticed over the years that the students coming in, they have a good grasp of basic knowledge. They are able to do what I call one-liner problems. And what I mean by one-liner problems, if we scan down here, these are some example problems that I assign as homework problems to college courses. And for example, under Ohm's law, number 4 there, what is the voltage across a 47 ohm resistor if the current through it is 2.5 amps? Just basic application of Ohm's law. I find that students coming in have no problem with that. But where they're having a problem is when we get beyond these little quick one-liner type problems and start putting that together into a complete circuit. So these first 2 pages I just put up as some examples of homework problems. Now this next one, this is actually an exam. And this is the way that I would write an exam. This is what I would expect students, whether they be sitting in the classroom here at Shawnee State, whether they're transferred in from other institutions, whether that be another college or career tech. If they were to take this exam, I would expect them to be able to show the same level of performance. So with that, let's start with this first problem. And obviously, when I start talking about DC, I start with the idea that I'm assuming that you know absolutely nothing about it. That's the way I start with my students. Now, you know, I don't mean to be talking down to any of you guys, because I know you all are educators and you have some background in this, but this is just to give you an idea of how I would present to the students. I would start off with the atomic structure. And of course, we know if we look at a basic atom, you've got the nucleus, which has protons, the positive charge. It has neutrons, which has a neutral or no charge at all. And then orbiting around that, you've got electrons, which has the negative charge. And then if we're talking about elements that would make a good conductor, there's different subshells. And within those subshells, you've got all these different electrons. And the further away from that nucleus you get, the less tightly bound that electron is to the nucleus. You can kind of think of it like a magnet in iron filings. Well, if we could somehow knock that farthest electron out of its orbit so that it goes over to another atom and start a chain reaction, that is current flow. And that's what we want to establish. And then I spend quite a bit of time dwelling with them what current is, what voltage is, and what resistance is. And voltage and current are not the same thing, even though a lot of people tend to use those two terms interchangeably. Current is obviously the flow of electrons through a conductor, and the voltage is the electromotive force or pressure that's causing it to flow. And then resistance is our opposition to that current flow. Resistance limits the current that flows through a circuit. Then I go on to describing what a conductor is and what an insulator is. Then we go to the wire tables, and I explain to them how to read the wire tables. They have that in their textbook. And with that, I point out that, you know, the larger the gauge number of the wire, the smaller physically the wire is getting, which means that if the wire is getting smaller in diameter, then therefore the resistance of it is getting greater as we go along that wire table. So those are all background information that I would have covered before they would get to an exam like this, obviously. We also have the use of meters on this exam, and we have the resistor color code on this exam. But let's just look at this first question. And we have a circuit here, and there's a lot of concepts that's covered with just this one question. Okay, it's obviously a series circuit. Okay, that brings up, there's three laws for a series circuit. First of all, to find the total resistance, you take the sum of the individual resistors around the closed loop. Notice resistor number 4. Resistor number 4 is just a tongue hanging in the wind there, just kind of flapping in the wind, not connected to anything. So if there is no current path, that means there's no current through it, therefore there'll be no voltage drop across it, so analytically we can ignore that one. We don't count that in the circuit. And thus we start talking about what an open circuit is. And one of the examples that I use about an open circuit, take for example a incandescent light bulb. I know they're getting a little bit old-fashioned at this stage of the game, but there's still a principle there. In an incandescent light bulb, there is a very fine wire called a filament. Looks like a thread. And as current flows through that, because the resistance of it is very high, it gets hot and begins to glow. Well, it doesn't melt because it's in a vacuum, and it glows and gives off light. Now, when a light bulb burns out, that filament breaks or becomes an open circuit. No current can flow through it. So that's why a burned out light bulb is an example of an open circuit. Yet I always get tickled if you have a tail light that's out in your car and you go to the garage and when they're changing your oil and you mention, hey, my tail light's not working, and they look at it and the bulb's burn out and they'll look at you and say, you got a short in it. Well, that's not true. That is a open, not a short. A short is a path that would bypass one of your loads in a circuit which then would be a short if, for R3, if we would take a piece of wire and just couple it in parallel with R3, then R3 would be shorted. In other words, we have a shorter path with less resistance rather than going through R3. Because current is like we are, it's going to take the path of least resistance. Okay, now as we go through this circuit, I can do this for you. All right, notice we don't know what the source voltage is, but it says C meter current. We don't know the value of R1. It says C meter current. Well, if we scroll down to the next page, you've got 2 meters there. I know they're sideways for you. But if we look at this is an analog meter. And I know I'm showing my age, but I'm a firm believer that we need to learn how to read an analog meter because anybody can read a digital one. With an analog meter, it's like learning how to drive. You learn how to drive a standard shift, then you can drive anything. Okay. R1 for problem 1. We have to read this meter. Okay, it is on the R times 100 scale. If I look up here for ohms, that's my scale that I use for resistance. Okay, and it is on the 2. That's 2 times 100 or 200 ohms. That's the reading on that. Now there is a 0 ohm adjust. Anytime you change resistance scales, you have to re-zero the meter to make sure that it is 0. To zero it, you put the 2 leads together on one of your resistance scales, and that needle should be on 0. If it's not, use the 0 ohm adjust to get it there. Then disconnect it. Also stress with students that you do not use an ohm meter on an energized circuit. It will damage the meter. Then we go over to this one, and we find our source voltage, okay, and it is on the 50 volt scale. And if we look right here where it says DC, that's that second scale down from the top. And that second scale, there's some numbers down there. And you'll see on those numbers, you'll see 250, 50, and 10. Well, we're on the 50 volt scale, so that 50 would project up. And here you would have 40 and 30 and 20 and so forth. So those numbers you're going to project up to the second scale, not the very top one. The top one is resistance, but the second one. Now, when you project those up, if we look at this one, where that needle is at, it's one little tick mark shy of being exactly halfway, which would be 25 volts. So one tick mark shy of that is 24 volts. Now, because it's on the 50 volt scale, that does not mean take that number and multiply it by 50. All that 50 volt scale is telling you that's the maximum voltage you can read on that scale. If you want to read above 50 volts, you've got to go up to the next scale. There is no zeroing required because it's automatically when you're reading current or voltage with this analog meter, it's already done for you. You don't have to zero it on that. Only on the resistance scales do you zero it. Okay, so let's go back to this first question. And over here, I've written it down for us. Our source voltage is 24 volts, and R1 is 200 ohms. That come from reading that meter. Then we've got R2. They have to know how to read the resistor color code. And I don't force students to memorize what each of the different color bands represent because I let them use their notes for that. My exams are open notes. They're allowed to use their notes on it. I expect them to understand how to read the resistor color code. If they forgot what value that brown represents, they can look that up. But here we have brown, black, orange, which is 1, 0, and 3. Now the first two is my value bands. That'd be 1, 0. And then orange is my multiplier band. So it is to the third, or add 3 zeros to that. That gives me 10,000, which is 10K. And then the tolerance band up here with no color on it. And I've got a note here, do not use the tolerance for any calculation. So you can ignore that one. Okay, so now we know this resistance value, we know this resistance value, and we know this source voltage. Okay, now, one of the rules of a series circuit to find the total resistance, you have to add up the individual resistances around the loop. So that would be R1 plus R2 plus R3. R4 is not in the loop. Plus R5 plus R6. And when we do that, we come up with our total resistance. Okay. And total resistance comes out to be 12K ohms. Okay, then I could find my current. Current, using Ohm's law, is equal to the source voltage divided by the total resistance. 24 volts divided by 12K gives me 2 milliamps. Okay, now, notice that these questions, you don't answer them in the order that they're written. Total resistance is one of the first things you have to do in order to analyze a circuit, and that's actually part D. And once you find part D, then you can go up here and find part C. Again, we are teaching the students to think critically, and they have to become analytical thinkers so that they can figure this out on their own. That's what I meant when I said earlier that I find students, as long as it's one-liner questions and I keep asking them that, if I would take the student and one at a time say, okay, now, how do we, if they knew how to read the meter, they could get that one. If they knew how to read the resistance, they could get that one. The resistor color code, they could get that one. Then I would have to lead them through and say, hey, now you got to find your total resistance. Now you got to find your current after you do that. I don't want to do that. I want them to be able to know to do that. Okay. I tell them working a problem like this is kind of like going to the all-you-can-eat buffet. Best thing you can do, with your plate, kind of scan the buffet and make a plan of attack. And that's how I approach these problems. You've got to get a plan of attack. You don't just start off with the very first question. Because sometimes you don't have enough information for that. Okay, now let's look at some other questions. Power for resistor number 5, voltage for resistor number 3. Well, I chose to find the voltage for number 3. Now, on finding the current, I used the source voltage and the total resistance. I applied Ohm's law to the entire circuit. Now I'm going to apply Ohm's law to one individual resistance. I is equal to V over R, therefore V is equal to I times R. So if I'm looking for V3, I would want the current, which is the same everywhere around the loop. That's the second law about series circuits. The current's the same everywhere throughout the loop. And multiplied by R3, the value of R3. So 2 milliamps times 0.33K is 0.66 volts. Now notice I've got 330 ohms, I've got 0.33K down here. I've got ohms, I've got K all mixed together in that circuit, so they're going to be converting from one to the other, moving decimal places and so forth. So that covers that aspect as well. Then we go for power. Power for resistor number 5. Well, P5 is equal to I squared times R5. That's one way of doing it. So I've got 2 milliamps squared times 0.47K gives me 1.88 milliwatts. Now, another way I can do it is find the voltage for resistor 5, which is the current through it times the value of that resistance, which gives me 940 millivolts. Then I can say that the power for resistor 5 is equal to the voltage of resistor 5 times the current. So multiply that by the 2 milliamps, I come up with 1.88 milliwatts either way. And I also stress with students, when you can work a problem a couple of different ways, work it both ways and see if you get the same answer. Use one as a check for the other one. So with that one question, we've covered a lot of territory. The third law of series circuits is dealing with voltage, and we know that the sum of the individual voltage drops has to add up to be the applied voltage. Now, we didn't cover that one in total with this particular question. Okay, I'm going to ask if there's any questions at this point.
Ken, I like what you're saying. This is Mark Jackson. I like what you're saying, particularly about, they have to think critically. Students have to look at some of this stuff, and it's more than just a one-line thing. They have to put all the pieces together. I'm actually wondering if you would mind if I took excerpts from what you're presenting here and actually showed my students, had somebody, hey, this is somebody that's teaching a class at college. This is what you're doing. Don't just take it from me, but also from you. I think that would be a powerful thing, but with your permission.
Yeah, I have no problem with that. I mean, everything that I'm putting out here, including my voice, it's free to do anything you want with it.
Okay. Awesome. Thank you.
Okay.
Hey, could I interrupt you? I don't mean to, but I did want to share with you guys, and I think I sent it in an email. There's a link to a tech prep website that has handouts and stuff that Ken has prepared, and they're extensive. And you are welcome to use those. So it was under my email where I was welcoming you to this. It wasn't the WebEx connection email. And at the bottom of that email, I gave you a link to a techprep.swOhio.org website. Click on Engineering Pathway, and you'll see the DC circuits, digital, just a wealth of information there. And the DC stuff was predominantly provided by Ken. And that's free for you guys to use. So go get it if you want it. Thanks, Ken.
Okay. Do we have any other questions? Okay, if not, we will continue on. Now let's look at the next example that I have here. Now we've got a circuit. We've got a 480 volt source. We've got a DC motor. It's a 30 horsepower motor, 88% efficient. The length of the wire connecting the source to the motor is 50 feet. That's all we know. We want to know the cost to operate the motor for 12 hours per day for 30 days at a kilowatt hour rate of 7.5 cents per kilowatt hour. We also want to find the current draw for the motor at full load. The wire gauge, being copper wire, required for the motor, and the resistance at 20 degrees centigrade, which that's the way the wire tables are set up, of that length of wire. Okay, what's our plan of attack? Well, I believe the first thing we need to find is the current for the motor. Now, I know voltage. I don't know anything about the resistance. And I know the horsepower output of the motor. And I know the efficiency of the motor. Well, percent efficiency is equal to power output divided by power input times 100. Well, if I rearrange that, I can find the power input is equal to the power out divided by the efficiency. So we've got a 30 horsepower motor divided by 0.88 efficient. That means I've got 34 horsepower going in. We know that 1 horsepower is equal to 746 watts. That means I've got 25,432 watts going in to this motor. Now, one of the concepts that we're looking at here is that the nameplate data on a motor is always your output or shaft horsepower. Electrically speaking, you have to put more energy in than what you're going to get out because none of them are 100% efficient. So that 30 horsepower, that is your output horsepower. It's one of the concepts we're stressing with this problem. Okay, so now that we know the power going into the motor, power is equal to V times I, so I can rearrange and solve for I. So I take the power in that we just found divided by the 480 volts, and I find I've got about 53 amps. Now, once I have that information, there's several different questions I can answer. The next one down, for example, we'll go up and do A next, or you could do C, it doesn't matter. While we're right there, let's take a look at C. The wire gauge required for the motor. Well, based off of current draw, a number 6 wire is up to 55 amps. And I'm pulling 53, so that would be sufficient. However, one size larger wouldn't hurt a bit since we're that close. But for the answer to this problem, I would accept number 6, or if somebody wanted to go up a size, I would find that. And then, if we go up here, the cost to operate this motor, we are paying for the power into the motor. A lot of students want to work this problem using the 30 horsepower. It'd be nice if you got to pay for it that way, but AEP doesn't like it that way. You have to pay for what's going in. So we take the power in watts, divide it by 1,000, we'll put that into kilowatts, times the 12 hours per day, times the 30 days, times 0.075, that would be 7.5 cents per kilowatt hour, and it's $686.66. Now, that sounds like a pretty expensive motor to operate, but those are realistic numbers. The 7.5 cents per kilowatt hour may not be, but the size of the motor, 30 horsepower. When we're talking about industrial situations, 30 horsepower is not all that big of a motor. Now, if we're thinking like most people think about in their home, I don't know if anybody's got a 30 horsepower motor at home, but again, that's one of the things that I've noticed with students. We live in a society that's less and less and less involved in industrial applications on a day-to-day basis. It used to be that, Dad worked in a industrial environment, and, we had dinner together and sit around the dinner table, and he'd talk about what he worked on throughout the day and this and that, and you got used to these kind of numbers. That's not so with students today. They don't have that, and they have no concept or no clue of what a 30 horsepower motor and the cost of operating that would be. I've noticed students, when we take them on field trips in industry, as soon as they walk through the door, they're just in awe of the size of everything. Because the only thing they have to relate to is what they see around the house. So I, early on, start throwing out some of these larger numbers to them so that they can get used to that. Okay, now this Part D, that's straight from the wire table. They have to look up on the wire table what, and the wire table is always listed in ohms per 1,000 foot. So then they're going to have to set up a little ratio, 50 feet times the ohms per 1,000 foot. And we come up with a very, very small number. But if you think about that, and when I give an exam, after they complete the exam, I grade it, I return it back to them, and then I put the solution on the board. And as I put the solution on the board, I'm actually going to lecture through it and bring out other concepts, and one that I would bring out here with this question about the resistance of the wire. That looks like a very small resistance. It's less than an ohm. It's a lot less than an ohm. But think about it. That wire, number 6 wire, is pretty good size. And we're only talking of 100 foot of it. So, you know, we're talking about a pretty good sized pipe, if you will. And how much resistance is there to water to flow through a big pipe if it's only 50 feet long? Very little. Well, the same thing electrically, if we're talking about the resistance of this electrical wire, and it is a large diameter wire, and it's only 50 feet in length, then the resistance would be very, very small. Okay, now I'm going to add. Yes.
There was a request to, if you could make your PDF screen a little larger or even make it full screen. Near the top of your screen, you got a percentage thing or that you could go up some. And then for those using the WebEx, right above where Ken is working right now, there's an arrow that points diagonally up and down. If you click that, it'll take his presentation screen and fill your entire computer screen. And then if you ever want to go back to the interface look with WebEx showing, at the top of your screen, you'll have a return button. So give that a try if you want. But either way, that looks a lot better too, Kim. Thank you very much.
That was a little bit better?
Yeah.
Okay, any other questions or comments at this point?
Ken, this is Mark Jackson again. I'm curious if where would this be along your class? Would this be kind of the middle of the semester? Would this be closer to the end, or would this be kind of first quarter time frame? Well, give me an estimate on where you would see this sort of content.
Okay. Our semesters are 15 weeks long.
Sure.
And we meet each week 2 hours a week for lecture, 3 hours for lab. So that's 5 hours per week times the 15. That's 75 hours. And then we've got a week for finals, which is another 5 hours. So there's about 80 hours of actual classroom-based time. Okay. And what I do is I divide the course, instead of just having a midterm and a final, I have exam 1 along about the 5th week, exam 2 about the 10th week, and then the final exam, you know, the 15th or 16th week. So this would be the first exam is what we're looking at, and the first exam goes up to this point where we just left off. And in fact, this is actually taken as one of the exams, exam 1, fall of last year.
Yes, indeed.
Okay, and then I'm teaching this course this semester, and they'll be taking their first exam on Monday. So that gives you some idea. We started the last week of August, and we're just now getting to the first exam. First exam goes through series, and then the second exam will cover series, series parallel, delta Y, Y delta transformation. And probably either mesh analysis or Thevenin's theorem, one or the other. And then the final exam, we pick up the Thevenin's theorem or mesh, whichever one we didn't get on the second exam, and we get into inductors and capacitors and magnetics as well. And that completes the course. One thing we do need to stress, this DC course, it's the foundation level. Everything else is built off of this. So it is very important that they have a thorough understanding. Every day up to this point, I start off my lecture with, okay, I'm going to give you a 3-minute review here. What is current? What is voltage? And I let them answer back to me. And what is voltage? And what is resistance? And what does resistance do? It limits the current through. And then I'll go over the 3 laws of a series circuit. Now, after this first exam and we move on to the parallel, then it'll be adding those 3 laws of the parallel circuit. And then your power equations. And once you get to that point, that's most of the course. Then from then on, you get into mesh analysis and your max power transfer theorem, Thevenin's theorem. Now you're just adding a little bit of finesse on top of the mainstay of the course. But Ohm's law and your power equations and laws of series and parallel circuits, that's going to haunt them from now on. I mean, it has to be that it is as ingrained in them as to, okay, what's your first name, you know. It has to be an automatic response, not something that they just have to think and think and think on. Thank you. Okay, any other questions? Okay, let's look at this. Okay, this next one we have a parallel circuit. Okay, with a parallel circuit, we're going to introduce 3 laws of parallel circuits. First of all, the resistance. To find the total resistance, it is product divided by the sum. It's always a good idea to check yourself. And one way we can do that is your total resistance is always smaller than the smallest resistance in the group of a parallel circuit. And then we have a little shortcut that we can do to find the total resistance. If you've got a group that's in parallel and they are all the same value, then you can take the value of one of them divided by the number of them that you have and come up with the total resistance. Now, this is a concept that you're going to have to spend a little bit of time with because it just doesn't really make sense when you first see this. Okay, the more resistors I put in the circuit, the less my total resistance becomes. That's true if they're connected in parallel. And one of the ways that I try to explain this is you think of your home water system. You've got your main water line coming into your home. Okay, downstairs in the basement, maybe you've got your laundry room set up. On the first floor, you've got a bath, you've got a kitchen, and then on maybe the top floor, you've got another bath. each one of those outlets, they're all connected in parallel. So if I have water that I'm using in the basement, and then I start using water in the first floor and water in the second floor, the more valves that I open up, the less resistance I have to that water to flow. And if you think of it in that terms, each one of these, okay, the more resistors, the more full paths that I put in there, the less total resistance I have, because part of that water can go this way, part of it this way, part of it this way, part of it that way. So that's one of the examples that I've used. I also show it mathematically, obviously. But let's look at this. Also, I stress that the students start the furthest point from the supply and just take them two at a time. Here we have 1.5K in parallel with 3, product over sum. 3 times 1.5 divided by 3 plus 1.5 gives me 1. Now check yourself. That total of those two should be less than the smallest one in the group. Well, it is. 1 is less than 1.5. Okay, now take that value and put your next one in there. 1 times 1/2, because I put everything in K, that's 500 ohms, that'd be 1/2 a K. Divided by 1 plus 1/2, that's 1/2 divided by 1.5 is 0.33 K. Getting smaller. Okay, now we're going to take that one along with this next one. 0.33 K times 1 divided by 1.33 K. And we have 0.25 K ohms for my total resistance. Now notice I put some dash lines in there. That normally wouldn't be in there. I did that as I'm working the solution. So I know at this point right here, I've got 1K. Here, I've got 0.33 K. And up here for the total, I've got 0.25 K. I'm going to use that in a little bit. So that's why I do it that way. Now, there is a law about voltages in a parallel circuit. The voltage across all parallel branches is the same. If I put a voltmeter from here to here, I would have 12 volts. Now, if I slide that voltmeter right over here, I'm on the same wire, still got 12 volts. I slide it over here, still have 12 volts. Slide over here, still got 12. Over here, I got 12. So the voltage is the same across all parallel branches. So V1 equals V2 equals V3 equals V4 equals the source voltage, which is 12 volts. That's because of parallel circuit. Now, let's find our source current, or total current, if you want to call it that. That'd be your source voltage divided by your total resistance. 12 volts divided by 0.25 K was 48 million. Now, this current, the third rule, dealing with parallel circuit, deals with current. And it states that the sum of the individual branch currents added up to be your total or source current. Now, those are actually Kirchhoff's laws. I just put it in my own words. But we have a handy-dandy tool here called the current divider rule. In the current divider rule, if we look at this, we look at a junction. Notice I've got junction A, B, and C. So we want to take a snapshot right there of junction A. Okay, here's my current divider rule. And at a junction, you've got your current coming into that junction. You look out this direction, you've got some resistance, and you look at this direction, you've got some resistance. If I want to know the current IX is equal to the resistance of this branch up here that I'm not looking for, right here on top, divided by the resistance in the branch that I am looking for, plus the resistance of the one that I was not looking for, then we take that and multiply it by the current coming into the branch, into the junction right here. IS is the current entering the branch. Now, in our example, let's look at a snapshot of junction A. Junction A, we have the source current of 48 milliamps coming in. Junction A, we've got 1K this way. And how much did we say we had over here? That's that 0.33 that we found earlier. There's 0.33. Now I can find I1 is 0.33K divided by 1 plus 0.33K times 48 mil. That's 12 milliamps. Okay, so now we've got 48 mil coming in. We've got 12 going this way. How much we got going over here? We got 36 going into junction B. At junction B, I've got 0.5K resistance in that direction. And right here, I've got 1K. Okay, here's the 0.5K. And back here, remember these two together, there's a 1K. So we go through that one. We find I2, 1K divided by 1K plus 0.5 times 36 mil coming in, that's 24 million. Then I go on to junction C. Now, about 36 mils that we had coming in here, and we said that we had 24 going here. How much we got left? We got 12 million coming into junction C. That's junction C. I'm looking at 3K in this direction, 1.5K here. So I3, that's down here, would be 1.5, the one I don't want on top, divided by 3K plus 1.5. Times my 12 mils coming out is 4 million. And I4, so go back up here, I found I3. So how much is left for I4? Well, I had 12 coming in, and I3 was 4. That means I've got 8 left for I4. So now I found all of my current. Now, to check myself, and this last scan here is, as I went through the scanner, it got twisted just a little bit. And the top should say I1 is equal to B1 over R1, and that comes out to be 12 milliamps, because it's 12 volts divided by 1K. I2 is B2 over R2, which is 12 volts divided by 0.5K, or 24 mils. I3 is 4 mils. I4 is 8 mils. Now, I found the current using two different methods. I used the current divider rule, and then I used Ohm's law. And we see that we have the same in both cases. So I use that to check myself. Okay. Which brings us to another good stopping point. Questions?
I have a question about your parallel resistance. This is Rod Pierce talking. We use the formula, or I teach the formula, the reciprocal, the sum of the reciprocals.
Right.
I assume there's no problem in using that. It's just a different way of coming up with the same thing.
It's just a different way of coming up with it, yes. I use this method because, you know, as far as meters and so forth, we're actually measuring resistance, and we can just use the numbers that we measure directly. But the receptacle or the reciprocals will give you the same thing.
Okay.
But I always teach it as total resistance is product over sum. Just using resistance, then I don't have to reciprocate everything. But I think that's basically a matter of preference. That's the way that I learned it,
Okay.
years ago. Kind of like, do you like a Porter or sugar the best?
Right.
They both get you there.
Okay.
This current divider rule, I teach it and I dwell on it and hammer that, because when we get into complex circuits, which is series parallel, it's quite convenient to what I call chase all your currents around the loop. And once you find all the currents, you can find anything else you want, whether it be voltage, power, or what have you. So it's a very important, very useful tool. Basically what you're doing is nodal analysis, because you're looking at a node and you're looking at the currents entering and leaving the node. Anybody else have any questions? And again, we're expecting students to be able to maneuver through these kinds of problems on their own without being led through, well, you need to find this first and so forth. Obviously, when we first start teaching it, we have to lead them through the very first time, but we expect them to be able to do this on their own by the time we get ready for the exam. Now remember, your students coming to us, they have this course entirety that they are transferring to us, so they're going to start off in AC, and we are assuming that they know all of this material and that they can do this type of circuit analysis on their own without being led through. It's a situation where that you're going to have to spend some actual face time with the students. You can't do it just by saying, okay, here's a module, complete the module, check off a couple of multiple choice questions at the end of the module, and then check the box that you've done and go on to something else. We can't get the depth and the rigor included if that's all we're doing. So we have to actually have some face time with the students. I'm a firm believer in using and utilizing labs. It's kind of hard to learn and understand this if you don't see it. And I actually have them hook up circuits using resistors, and we use meters, and they use the resistor color code. They calculate what it should be, then they measure it, and I have them measure it with an analog meter, I have them measure it with a digital meter, and we should come up with the same results through the color codes and calculations and both types of measurements. Of course, we realize that there's tolerance on all the components, but beyond that, should have the same answers. I've got a thought question that I've put on here, and this is one that I've used quite a bit. This happens to be off of a multiple choice portion of an exam. If you have 10 light bulbs in parallel and one bulb burns out, the result is, well, first let's ask that same question and strike the word parallel and put series. If it's a series circuit, what's going to happen? Well, obviously it is a break in the current loop, and therefore no bulbs would light. Now, let's go back to the way it's written in a parallel circuit. And my choices are 9 bulbs with greater brilliance each, 9 bulbs with less brilliance each, 9 bulbs with the same brilliance each, or no bulbs will light. Well, the correct answer would be 9 bulbs with the same brilliance for each bulb. I find it amazing how many students will always pick A, 9 bulbs with greater brilliance. And I ask them, okay, if you're sitting at the dinner table and you've got a nice chandelier light overhead, and there's 9 bulbs in that chandelier, or let's say there's 10 bulbs in that chandelier, and one of them burns out, does that mean that the other 9 automatically get brighter just to make up the difference? I don't think so. So we end up with 9 bulbs with the same brilliance. It's not going to affect the remaining 9 bulbs. Just the one is no longer putting out any light. Okay, that completes what I had prepared as far as a lecture. I wanted to give you an insight of what I would expect students to be able to do. I want to spend some more time now discussing the rubric. I assume that you're all familiar with the TAG rubric. We want to talk about that a little bit. And just in general, the idea of the career tech students coming out of your course with the same level as what a college course would include. So at this time, I'd like to try to get a discussion going back and forth and invite everybody to participate. On your rubrics, you've got your objective, and then you've got applied skills, and some applied skills, little applied skills, and minimal applied skills. Well, obviously, it would be nice if in every category that we could be over on the applied skills strongly demonstrated. Well, maybe that's a little bit high on the wishful thinking list, but I would certainly think that at a college level that the lowest you should have would be some applied skills demonstrated. We've got to get beyond the minimal applied and the little applied demonstrated. Those first 2 categories is what I consider high school level, and the 2 upper categories on the college level. At the college level, when you get up into the last couple of items, the MASH and the nodal, and also looking at properties of inductors and capacitors, perhaps they might be on the next to the highest level, but certainly on these first few objectives, they have to be at the highest level in order to be able to complete the upper, more rigorous topics. And keep in mind that all of these topics are required to meet the tag. Okay? It's not, some of the tags in some of the other areas, you have a list of tags and maybe you've got 10 topics and you have to meet 7 out of the 10. Well, it's not so with the DC course. The DC course, you have to meet them all because it's a foundation course, and the AC course, we're making the assumption you already know all of this and that you have mastered it because you're going to apply it in the AC course as well. Okay, I'm open for comments or questions.
Hey, Ken.
Yes.
I'm so sorry. I didn't have my screen on your display. I was just listening. Did you actually show the rubrics, what you were talking about?
No, I don't have the rubrics on my screen.
No problem. If it's okay with you, do you mind if I show them that website and the resources that are out there?
Yes, go right ahead.
Okay, I'm going to take control then.
Okay.
Let's see, Terry, you may have to switch me. I think you can switch control. Can you just click on the first Terry Benedict, not the one that says host?
Okay, well,
Click next to the name. For some reason, it's not letting me. Perfect. Okay, can you click on the other Terry Benedict?
Okay.
Terry, are you still there? Are you still connected? If not, Ken, I'll ask you. Well, actually, Terry, can you just connect me to, just slide the blue ball to me so I have control? Next to our name.
I just gave it. Okay. Did that work?
Let me see here. Yeah, it's not on me right now.
It's on you without second.
Oh, is it? Okay. Okay, Terry, there should be two Terry Benedicts.
Okay.
My Rob Speckert one is my tablet. I was just kind of observing on that one. If you can click on the other Terry Benedict. Maybe it's not coming, Terry.
I thought I transferred it to you.
Huh. Sorry, I'm not seeing it.
Are you in the first drop?
No, my login is Terry Benedict, Terry.
Okay, let me move this then to that.
Okay, perfect. There you go. Oh, perfect. Thank you so much.
Sorry.
That's okay. All right, so here's my screen. Actually, I was working on that test. But I wanted to show you, if we go to that website, and bear with me just a second because I got a whole bunch of stuff open here. So I'm going to go to this website, www.techprep.swohio.org. You can see that here. And if you hit enter on that, so just come over here to the engineering pathway. Sorry, I didn't mean to hit it that quickly. On the right-hand side is engineering pathway. If you select that, it'll take you to the resources for rubrics and class materials and so on. So Ken's work is in this region. And so the rubrics for DC circuits are right here. And again, this is a PDF document, so you can save it to your desktop or print it. In fact, that's true for all the documents. But what Ken was talking about, as you cover some of these topics, you probably, for most colleges, especially for courses like DC circuits, I would suggest that most of them are over in this region here. In this region here. If you find yourself covering the stuff over in this region, and again, this is using what's called Bloom's taxonomy or levels of knowledge, you want to push to move this direction. And this gets more detailed as you come down through here, and this becomes very specific as you work your way through here. Okay, so that's the rubrics that Ken had made reference to. Here's Ken's syllabus, and you're welcome to use that. And then we did some of this workshop stuff in preparation for this material at other tech prep sites across the state. If you follow this link, it'll take you to a duplicate of this stuff, but then even more material down through here. But so, for example, some of the stuff that Ken has provided, basic stuff on Ohm's Law, and most of these, again, are PDF documents. So feel free to use them. And I think Ken displayed several of these. Kirchhoff's Law, some of these things he's going to be talking about in subsequent courses or presentations here.
Yeah, those are a couple of the labs that we actually use.
Yeah, we lost you there in the end, Ken, if your audio.
Oh, okay. The last two slides you had up there show some of the labs that we actually do in the course.
Okay, so this is the Kirchhoff's voltage lab.
Mm-hmm.
And you'll probably be talking about these in subsequent things.
Right.
So I don't want to steal your thunder, but
oh no, this is fine. This is fine. I figured this first night I kind of kept it light because I thought we would have more discussion on the rubric.
Absolutely. Oh, and this is perfect. So, folks on the connection, just know that guys like Ken have provided this stuff and agreed to make it available to you. You're welcome to use it. Again, they're mostly in PDF format, so it's probably not so editable. And if you want even more stuff, again, without overwhelming, you go here. Hopefully that link works. There it goes. Again, little duplication here. But here's even some more stuff, and this was provided by a gentleman from Rhodes State. So if you click on any of these, he's got quite a bit of stuff here. And it continues down. He also does a lot with, he has a lot of review handouts. Dave Schaefer does at Rhodes State. He uses a lot of self-written things that students use as guides, and that's what many of these things are. So again, I'm not going to go into those in great detail now, but you have access to all this through this connection.
Hey Rob, Adam Paisley here. I've just got a quick question.
Yes.
As a new guy, what is the difference between a tag and a C tag? I see that you have links for both.
Yeah, that's an excellent question. I'll tell you what, the idea is that I'm going to take you there and show you a little bit of, well, let me just talk with you briefly about it, and then we'll go from there. So I'm going to just come back here. Sorry, I didn't mean to not share here. But if you, the idea is that a tag, the term tag means Transfer Assurance Guide. And what it is a college-to-college guaranteed movement of credit from one college to the next. So if you go to www.ohiohighered.org, ohiohighered.org, you don't really need the www in front of that. And you go to educators here. If I go to credit transfer, so I went to educators, credit transfer, over here describes those things. So transfer assurance guides are really a takeoff of what's first called an Ohio transfer module. An Ohio transfer module is a block of 33 semester credit hours approximately that all colleges across the state of Ohio have. And basically it says this: you're guaranteed as a student that if you take that block of credits at Zane State, at Marion Technical College, at whatever, North Central State College, whatever college, Miami, UC, at every state's college, you are guaranteed that that block of credits will transfer to the receiving institution and apply towards graduation requirements. Transfer assurance guides take the idea of the Ohio transfer module and breaks it down into curricular areas. So what I did is I clicked on transfer assurance guides, and these are categories of courses for which tags have been developed, and I'll show you engineering technology since that's our area. And you can see this is guaranteed college-to-college movement of credit from one college to the next. So for example, if a student takes AC circuits at Shawnee State University and wants to transfer it to Miami University, if I go into this system, it'll tell me the course at Shawnee State that is tag approved for AC circuits. And it'll tell me the course at Miami University that's tag approved. So that's where the alignment comes in. In other words, Ken at Shawnee and his colleagues submitted their AC circuits course to a database and mapped it against the requirements for an AC circuits tag. Miami did the same thing. Now a student wants to transfer from Shawnee to Miami or Miami to Shawnee, it doesn't really matter. They're guaranteed of those course numbers. And there's a lookup system within the tag that shows you which courses those things are mapped to. In fact, it's right here. So I'll show you that, for example. So here's a tag. So tags are college-to-college movement of coursework. So I'm going to select a course equivalency. I'm at Shawnee State University. I want to go to another university, but you know what? I'm not sure where I want to go. I'll leave it as select all. But I know that I did it in electrical engineering technology. That was my area of coursework, DC circuits, AC circuits. And I just finished that here in spring of 2015. Show me where I could go across the state of Ohio. So these are coming from Shawnee State, the courses at colleges across the state of Ohio that a student could go to. So again, these courses over here, there's the DC for Shawnee, there's the digital and so on. And these are the destination institutions. So if I sort this by course number, let me sort this the other way. Here's all the digitals, and there's all the digitals across the state of Ohio that it would go to. So there's their course number at Shawnee. There's electronics. So then what happened was the Board of Regents said, okay, let's take this same principle of applying credit and making sure there's equivalencies, and let's apply it to career centers.
Hey, Rob?
Yes?
Real quick, before you go any further, I don't know if anybody else is having the same issue, but I'm not seeing what you're doing on the whiteboard.
Oh my gosh, I am so sorry, and thank you.
Okay. That's okay. I've been tracking what you're saying, and I've been following along online.
I'm so sorry. I stopped sharing my screen and forgot to go back to sharing it. As much as I use this darn thing, that stupid stuff for me happens all the time.
There we go. I see it now.
Thank you very much. So I'm at ohiohighered.org. I clicked on Educators Credit Transfer. That got me to this screen. And then I clicked on Transfer Assurance Guides, and this is where I had the dialogue. I was basically showing the descriptions, the equivalencies, and so on. But you can actually see the equivalencies right here. Okay. And rather than do it again, I know, like you said, you were following along. I'm going to take you to where you can do it with C tags, because this is where the power comes in for you all. What happened was the Board of Regents and faculty across the state said, hey, let's take this principle of alignment of credit and let's apply it to career technical credit. So the initiative called Career Technical Credit Transfer, CT squared, happened. And so here's CT squared, and this is what we're all about here in this workshop right now. So these are all the areas. If I go to this description page, and I did a similar thing when I was under tags. So I'm giving you a really long answer to a short question. Tags are transfer assurance guides. It's college-to-college movement of credit. C tags are unidirectional movement of credit from a career or adult center to a college. These are the areas of eligible C tags. So not all areas apply. But we're working right now here under electrical engineering technology. And if I click on this, and this has just been updated, There's DC circuits, digital electronics, and programmable controllers. Now the workshops we're running right now are only covering these two. We're doing this one first, and we're following it up with digital. And the reason we didn't do PLCs is because very few career centers get equivalency credit for PLCs. Adult centers, maybe so, but not so much career centers because the outcomes are so detailed. But all these documents are written the same, little executive summary, scroll down, and here's the outcomes. So what Ken was talking about, when we looked at the rubrics, what we saw was we developed rubrics that said, okay, what do we mean when we say these terms here? What do we mean? And that's where the rubrics came in. We gave details behind that. And then the next course we're going to do in this series is going to be digital. But here's PLCs. Again, we aren't going to actually do a workshop for those. And then here's the people who've been involved with this initiative across the state. Okay, so let me show you how powerful this is. So I'm back to the CTAG website. Here's the main CTAG website. There's the link, www.ohiohighered.org/transfer/CT2. Check this out. If I go to this approved programs and courses, and I go to CTAGs here, so now I want to know what are my course equivalencies. So I'm here at Butler Tech, let's say, and that's a school near me. And I want to go to a college. Here's all the colleges that are participating. By the way, they're all the state schools. If I leave select all, it'll show me all the equivalencies. And I'm going to do, actually, I'm not sure they have an electrical course, so I'm going to come back to, I don't want to come up with a blank screen here. I'm going to come back to Hamilton where I know. I'm going to say, I want to see what happens at all colleges, and I want to do it in electrical engineering technology. And I'm finishing up here. I just finished in spring. If I do a search, this is me coming from Hamilton City Schools, and these are all the colleges and their course numbers for which I could receive college credit. So these are DC circuits here. In fact, it looks like Hamilton only has approval for DC circuits. So there's the Shawnee State course up here, Northwest State, Stark, Terra, University of Akron, University of Cincinnati, Washington State, Miami University. These are the actual course number at the college that the student would get credit for. What a powerful tool.
And if I may interrupt here just for a minute, that brings back when I started and said that it requires a mindset change from the instructors at the Career Tech Center that I'm teaching a college level course, because in essence that's what you're doing. You saw that from that one Career Tech that the student could get college credit at all these different institutions with that course number. So they're walking in the door, I've already had this course, I've got credit for it. Well, then that means that the knowledge that you're bringing in the door has to be the same. So as a Career Tech Center instructor, you have to keep that in mind. You're teaching at the college level on that course.
Great. That's awesome, Ken. And what I did here is pull up all the schools across the state that have some courses approved in electrical engineering tech. And you can see it's career centers as well as colleges. So at your school, if you've not received this approval yet and you want to get approved, in other words, after you look at this rubrics and stuff, you say, hey, we cover that, then I can help you submit those courses for approval. And we would obviously do that outside the context of what we're doing here.
All right, great. Good to know. Thank you.
Good. Yeah, that excellent question, and thanks for asking the question. I did want to point out that the actual method for the student to receive approval, there is a process that needs to be followed, and maybe at a subsequent connection, we may want to talk a little bit about that, but there's a device, a tool called a credit verification tool. You know, when you ask about tags, the college-to-college movement of credit, man, it's as seamless as you'd ever want it. The universities have a really well-established transcript system that basically all the colleges and universities follow. So when moving credits from college to college, it's really simple. But moving credits from a career center or a high school to a college, there's not a standard transcripting system. So it's kind of clumsy right now. And there's a tool called a credit verification form that needs to be completed by you as a teacher, validating that your student completed a particular CTAG equivalent course. And of course, your school has to be approved for it too. And we can talk about that one-on-one or maybe in another session or something. Okay, I'm going to stop sharing mine. And again, thank you for speaking up. I feel terrible that I went for several minutes there without resharing my screen. That was dumb. By the way, and I like that you spoke up. That's important to do in this kind of stuff. I know that in my classes, because I use this for my class on Thursday night. I teach senior design strictly by WebEx, and you'd think I'd remember to do half those darn things, but every once in a while you forget. So, Ken, did you have anything else?
Okay, I just wanted to ask if anybody else had any questions about the DC Circuit course specifically. Next session, which will be Thursday, I'm planning on going through the complex circuits, which is series parallel and Y delta delta Y transformation. That's going to be the topic for that. And basically what I'm attempting to do is highlight everything that I do in the DC course in the 5 sessions that we meet. So we're going to do it in 10 hours, what takes me 75 hours to do in the classroom. So I'm compressing it considerably, but I'm trying to highlight the topics, and I want to keep it very informal. Anytime you've got a question, my intent is I'll talk for a few minutes and then I'll ask for questions, and feel free to join in, and we can make this a two-way communication here.
Well, I think for our first cut, this went pretty well, Ken, and I'm excited to hear some of the other stuff you're going to be doing. Anybody have any last parting thoughts? Carrie, did you have any comments?
I really appreciate all of the efforts that you've been doing, and I think that this is going to be a great venue for us to disseminate information. Thanks so much, Ken. I know you were a little nervous since this is your first attempt at this, but you did a great job.
Well, I gave it my best shot here. Like I say, I've got well over 30 years experience on the circuits end of it. I don't have a problem with that, but the WebEx, this is new territory.
Good job.
Yeah, I think, too, Terry Benedict has, just been a tremendous resource and supporter of this initiative. We started with what we called GAP workshops, mini presentations by guys like Ken, and now it's morphed into this almost pseudo-class thing. The whole spirit of this is what Ken started with, and that is to share technology, share teaching strategies, share information, so we're all on the same page. And feel free to pick the brain or, question or say, hey, let me show you an idea I have, or whatever. I mean, that's what we really hope comes out of this thing. And you guys have been great.
I have one other thing to share. You mentioned sharing there and what you were just saying. For a long time, I've had a difficult time with getting students to understand the difference between the mathematical units, say 1 ohm versus 1 K ohm. And it's like, you just have to pound it in their head that K is 1,000. But beyond that, if we're talking about an amp versus a milliamp, well, how much difference is it really? Yeah, we can show it mathematically. We can move the decimal point 3 places. But do they really understand that? And I also work on the mechanical side of the arena here. And one day it hit me. And so I brought a micrometer into the electrical classroom. And I said, I want to show you the difference between an amp and a milliamp. So I had a 1-inch micrometer, and I opened it up all the way to 1 inch. There's my amp. Then I closed it down to 1,000th of an inch, at which you had to hold a light behind it so that you could actually barely see the gap. Now there's my milliamp. And it made a vivid picture of the difference so that in their mind they can actually start to understand it. Just seeing numbers and decimal points on paper, a lot of times we still don't get the full effect of the difference of it. So I thought you mentioned the word sharing there, and that's just something that I come up with, and I'll throw that out there to share.
That's great. Anybody else have anything they want to mention? If not, I guess we'll conclude this.